Okay, our next talk is from Miguel Montero, who's going to tell us about the Festina Lente bound and its Pheno implications. Take away, Miguel.
Okay, you guys can hear me, right? Yeah. So thanks a lot, John and Cody, for putting together this super nice seminar series. Like, you really have kept the community together during COVID times. And thanks also for the opportunity to speak here and tell you about some recent work that I did in collaboration with Kumrum, Thomas Van Riet, and Herben Benken about the Festina Lente bound and mostly about its Pheno implications. So of course, I first need to tell you what the Festina Lente bound is, but even so, I like to start. I like to do that by putting it in the bigger context of where does the Festina Lente bound come from in the bigger swampland picture, right? So the main idea of the swampland is that you try to assert universal features that quantum gravity might have, which are kind of like model independent. And of course, we cannot really prove anything rigorously in full generality because we don't have a framework to prove things in quantum gravity. But we have learned quite a bit over the past few years, and we have organized this knowledge into a way of interconnected conjectures. So if you want to learn more about this, there's a bunch of reviews, and this is the most recent one. You could also watch Irene's review talk at Strings from 2 weeks ago. So there's by now a huge landscape of conjectures, and they have very strong support from string compactifications. And the Festina Lente bound that was in my title slide is in the orbit of arguments and conjectures around one of the oldest swampland constraints, which is the Weak Gravity Conjecture. Okay, so the Festina Lente bound arises when you combine this tried and tested Weak Gravity logic, which I will review in a moment, and you take it away from, you take it on a trip away from home. You apply it in a setup where it's usually not applied, which is to the context of black holes in situations where you have positive vacuum energy, like the sitter, or like a slow enough runaway. So when you combine these two things, you get a new constraint on the charged on the spectrum of charged particles in the theory, which is has very interesting Pheno implications, and that's the bound. So I'm going to be telling you briefly about how to get the Festina Lente bound. I'm going to be kind of telegraphic. You can ask me questions afterwards, or you can also watch Herben Benken's talk earlier this year in this very same seminar series, where he gave quite a lot more details on where does the bound come from. Okay, so what is the Weak Gravity Conjecture? I told you this comes from Weak Gravity ideas. Weak Gravity tells you that in a consistent quantum theory of gravity with a U1, you must have charge states which are light enough compared to its charge. And we have extensive evidence for this coming from all sorts of stuff in string compactifications. But from my point of view, even better than that, we even have like a physics reason why something like this should happen. So already in the original Weak Gravity paper, they noticed that if you impose this kind of thing, then you ensure that non-supersymmetric black holes are able to decay while remaining, that's a typo, it's a bad typo actually, sub-extremal. Okay, so they do not become super extremal. And we have this can be substantiated with arguments coming from non-global symmetries, and more recently there's been a connection. There's been papers showing that there's a connection to this to cosmic censorship, and I also had this work trying to connect it in the context of ADS-CFT to basically the ER-EPR proposals. So there are reasons why it's reasonable to believe that black holes should decay while becoming sub-extremal. And what we're going to be doing in this talk is just take this principle and just apply it to black holes in the situ space. So briefly, what happens in flat space is if you draw this, draw the mass versus charge plot. So the picture you have in flat space is something like this. You have some extremality condition for the black holes, for charged black holes. Rising order for charged black holes is typically a line in the minimal theory, and then so if you have a Weak Gravity particle which lies on the other side of the line, then you make sure that black holes here can evaporate little by little all the way and disappear, while never crossing this line, never crossing the extremality line. So all sub-extremal black holes lie on this side of the line. So what we're going to do next is do the same thing for charged black holes in the situ space. Well, so this is the plot that I had for flat space case. And if you're doing in the sitter, well, you need to take into account curvature corrections to the black hole extremality bound. I mean, it's not unreasonable. I mean, it's what you would expect, right? When the black hole becomes big enough to really sense the cosmological constant, the geometry is going to react, it's going to change, and it's going to change the extremality bound. And, you know, it just changes in this way. It bends upwards. So that's fine and well. And not too surprising. What is surprising is that if you analyze these black holes carefully, you find that this curve here doesn't go all the way to infinity as it does in flat space. It bends over and joins back the region with zero charge. So in the sitter, the allowed region of subextremal black holes, non-singular black holes, is bounded. For each value of the charge, there's both a minimal mass, that of the extremal black hole, and a maximal mass. And there's a very simple physical way to understand why is there a maximal mass. The black holes, you know, the sitter and quintessence-like scenarios, they all have a particle horizon. And so very naturally, you cannot have a black hole which is bigger than the particle horizon. So there's such a thing as the biggest black hole that fits in the static patch of the sitter. And that's precisely this branch of black holes on the right-hand side, which is called the Runaway branch. And they have a near horizon, the sitter 2 crosses to geometry. So ordinary weak gravity comes from asking what happens, you know, about the black hole, which is here, and demanded it evaporates without crossing into this region. And what we did in the first Festina Lente paper, and which I'm not going to review in detail, is to try and ask the same question for a black hole, which is here instead, which is on the Runaway branch. How does it evaporate? That's a GR problem, GR plus quantum Euclidean curve spacetimes, and you can just solve it. Take some effort, but you can. And what you find is that depending on the effective field theory that you have, depending on the properties of the charged particle spectrum, it may happen that the black hole doesn't evaporate while remaining subextremal. It can do something like this. It can discharge too quickly. And if it discharges too quickly, it becomes super extremal. And, you know, by just extrapolating, as I told you, we're just going to extrapolate the principle that we have tried and tested in so many setups. And we're going to take it a little bit out and see what it implies here. And if we just take seriously the idea that black holes cannot become super extremal, then it just follows from the analysis that you must impose a bound which is similar to weak gravity, but which goes the other way around. So it's a lower bound on the masses of charged states. It's telling you this is the bound for a state with charge 1. With charge q, you will have a q squared on the right-hand side. It's just telling you that the mass is lower bounded by the product of basically the vacuum energy and the gauge coupling for every particle in the theory. Okay, so this is the main character of the talk. This is what we call the Festina Lente bound. There's a reason for the name, and I can talk about that later if you ask. But yeah, that's basically the bound. It's a Swampland bound, just followed from weak gravity logic. And for the rest of the talk, I'm going to be, you know, treating this Festina Lente bound as we treat any other Swampland bound, like asking what happens to it in a bunch of different scenarios, and also trying to work out these phenomenological implications, which are pretty interesting. So the first thing that one should do, which we didn't do in the original paper, we did a little bit only, is well, this Festina Lente bound with these plots, with this shark fin that I was drawing, strictly speaking, was only derived for positive vacuum energy for the sitter. So the first thing that we did was to generalize the Festina Lente bound to situations where you have runaway potentials. And we just argued for Festina Lente from physics of narrow black holes. So you will have an argument for the Festina Lente bound whenever narrow black holes exist. And it turns out that if you have a situation where with a runaway potential and possibly a gauge coupling that also depends on the value of the scalar, which is running, narrow black holes do not always exist. They only exist if you satisfy a couple of consistency conditions involving first and second derivatives of the potential and also the gauge coupling. Okay. If these conditions seem to look a little bit like the de Sitter conjecture, or the kind of conditions that we're talking about the de Sitter conjecture, that's because they are. The narrow black holes, they're extremal black holes, so they have a near horizon geometry, which is exactly the de Sitter 2 cross S2. So Festina Lente applies whenever you can construct a de Sitter 2 solution in your theory. Now, that automatically means that in many interesting setups, in fact, mostly everywhere in asymptotic regions of moduli space that we know in string theory, you should not apply Festina Lente because we have no-go theorems for de Sitter, and they often apply also for de Sitter 2. So for instance, you might wonder, should we apply Festina Lente for the SO16, SO16 string? And the answer is no, because these conditions are not satisfied, which is good, because the SO16 SO16 string has massless charged matter. So it would violate the Festina Lente bound if it did apply. So in this simple way, it is consistent with most of the string with most of the string evidence that we have, but not in a very interesting way, not in a way that we can check precisely in asymptotic corners in modal space. If anything, it's going to be an interesting statement in the bulk, and I will come to that later in the talk. Okay, so that's one thing you can do with Festina Lente, which we did to generalize it to scalar situations with a scalar potential. And another very simple thing that you can do, and it's very natural, is, okay, suppose that you're in the kind of situation where the Festina Lente bound applies, like this, then you will also expect that the weak gravity holds. So what happens when you get the two of them together? And what happens is that you get a lower bound on the gauge coupling in the sitter. It's a precise lower bound with a precise numerical coefficient. It is, on one hand, it's not that surprising, because this is kind of what you would get from just the magnetic weak gravity cutoff is bigger than the Hubble scale. You would get something like this. But on the other hand, it's pretty interesting, because precisely this same bound was derived independently in one of the first papers that came out after the original weak gravity paper. What these guys were doing, they were following the original. So in the original weak gravity paper, there's the argument for the electric weak gravity and magnetic weak gravity, and the magnetic argument is very different. It's about having a monopole and the monopole not being a black hole. So what these guys realize is that if you have this magnetic argument in the sitter, it should also impose that the monopole is not bigger than the cosmological horizon. Otherwise, you cannot have a monopole at all. And because of the properties of the narrow black holes, you can actually be sharp about the gauge coupling, and that's what you get. So it's the point here of this slide is not that you have a lower bound on the gauge coupling, which, although interesting in itself, you don't need to talk about Festina Lente to get. The point is that what you get from making an argument about electric black holes and an argument about magnetic black holes, both things tie in together very nicely. And this just in the same way that they do for ordinary weak gravity conjecture. And this just didn't have to happen. Could have failed. So we find this, I find this interesting. So more stuff that you can do with Festina Lente. You can ask how it, another thing that we've done with the weak gravity conjecture, and it's important in our belief that it's consistent conjecture, is to ask how it behaves under dimensional reduction. And this has been done prominently by Ben Heidenreich, Matt Rees, and Tom Rudilius, and particularly by Tom, actually. So we were just doing the same thing. What happens if you start with a d+1 dimensional theory of pure gravity, put it on a circle, and then ask if the Festina Lente is satisfied for the Kaluza-Klein photon? Well, the d-dimensional potential has two contributions. There's one of them is a Casimir energy coming from stuff running in loops, and the other one is the tree-level contribution just coming from the bare cosmological constant in one dimension more. And it turns out that you can actually study Festina Lente in two regimes. In the very large radius regime, where this thing is negligible and the radius is not stabilized, it turns out that the inequalities that I put before are satisfied. So you get to apply Festina Lente. And so you can study it there, and it's just satisfied. And in the other scenario, where you actually play this term against this other one, so that they produce a non-trivial minimum, like we do, for instance, in the standard model, what you find is that Festina Lente provides a consistency condition, which is that the radius of the internal dimensions has to be smaller than Hubble radius. So this is again nice. What you get from Festina Lente for Festina Lente 2 is telling you is that if you're having after dimensional reduction, for it to be consistent with the Festina Lente picture, it's just that you have some sort of this is the basic condition you should impose in order to just to have a valid effective field theory around the sitter. So that's what you get. Another thing that you can do is just start with a U1 in d+1 dimensions, and then you have d+1 dimensional version in Festina Lente. And so you can ask, is this preserved in the dimensional reduction? What happens when I put this here in a circle and I get a U1 in d dimensions? And you can just check. And the Festina Lente bound for this kind of U1 is exactly preserved, by which I mean, if you have a particle saturated in Festina Lente in d+1 dimensions, then the same particle, the zero Kaluza-Klein mode of that particle, also saturates Festina Lente in d dimensions. Okay? So that's again nice consistency check of the proposal. And actually, we have a lot more stuff in the paper. So we have a tower version of Festina Lente. We also did like a convex hull generalizations to multiple fields. We also asked what happens when you have a higher p-form field in d plus p dimensions and reduced to get a u1. We also discussed what happens to the Festina Lente argument when instead of electric charge, you have rotating black holes. And again, everything is consistent and it works out nicely. So you see, the kind of picture that we have for Festina Lente right now is that it's something that you cannot really check very strongly in compactifications, but there's a lot of checks that could have gone wrong, and they don't. So there's this thing. Lots of standard swampland checks like this. But for the rest of the talk, I'll actually like to focus on Pheno implications of the Festina Lente bound. Well, so that's the nice thing, right? So there's like a bright side and a downside. So the bright side about Festina Lente is that you get to apply it to the real world, even if you cannot check it in string compactifications, because the real world precisely has positive slow rolling vacuum energy and a U1, which furthermore we know is not the electromagnetic coupling is also not changing appreciably over cosmological timescales. We have actually measured this kind of thing experimentally. So Festina Lente applies, and if you just rearrange it, what you get is a lower bound on the cosmological constant. Sorry, an upper bound on the cosmological constant by the masses of any charged particle in the theory. And so, in a sense, Festina Lente is relating the cosmological and electroweak hierarchy problems because the masses of these guys are, they're coming from the Higgs. So, so this is the correct bound, and if you just evaluate it numerically, just put here in the electron mass, you would get a prediction that the cosmological constant has to be less than 10 to the minus 88 in Planck units. Now, this is still 30 orders of magnitude away from the measured value of 10 to the minus 120. But, like going 90 orders of magnitude, I'd say that's a reasonable good job for just swampland argument coming directly from black hole considerations. And, just to show you the same information in a slightly different way, this is a logarithmic plot. This is done to scale, actually, with, the Hubble scale on one end and Planck on the other. The Festina Lente scale is kind of in between. Is the geometric mean of the two. And you can see that the masses of charged particles, they sit comfortably on the right hand, to the right, which is what the Festina Lente bound would require. Now, to bridge this gap between the electron and the Festina Lente bounds, what we would like to make a prediction that would be kind of saturated is to have a particle which is charged and it has almost the mass of a mass saturated in the Festina Lente bound when you substitute the observed cosmological constant. And of course, we know one such particle, that's the neutrino. The only problem is that it's not charged. So we can directly apply Festina Lente arguments. But if you did, you could explain the 10 to the minus 120. Now, we've spent a lot of time trying to argue that you can, apply Festina Lente anyway to neutral stuff. You could imagine, for instance, that B minus L is a spontaneously broken gauge symmetry in the standard model, and maybe Festina Lente still applies to broken U1s, and then you would get an argument. But we couldn't make any of this work because, like with spontaneously broken U1s, you didn't have arguments with black holes. So let me tell you briefly about a scenario for Festina Lente microphysics that naturally also incorporates neutrino masses. So what do I mean as scenario for Festina Lente microphysics? When you look at other swampland constraints like weak gravity, they're just constraints in effective field theory, which don't have like from the point of view of effective field theory, there's not a really good reason for them to be there. But then if you really have access to the 10-dimensional string model, you can say, oh, I see this, the weak gravity is happening because this cycle is small enough so that the mass of the state is light enough. So there's a microphysics reason for why this kind of thing happens. And so what I wanted to tell you is a scenario that we came up with in which Festina Lente is automatically satisfied, and you also get kind of like neutrino-like states. It might not be the reason why Festina Lente is satisfied in actual models or generally, but it's an interesting scenario, I think. So the scenario is, of course, for Festina Lente, we need a positive vacuum energy. So we just imagine that we had some sort of Bose-Polchinski mechanism. So we just have a top form, which is just like generated vacuum energy because of its integer value of field strength. And when you have a scenario like this, you also have domain walls that allow you to, change the value of n. Typically in string theory, when you get these domain walls, they also come with warp volume couplings of the Chern-Simons type. So what we assumed is that we have a vacuum energy supported by fluxes like this. Also, we have a massless U1 field in the bulk, because of course, Festina Lente only makes sense when you have those. And what we imagined was that the membrane had a warp volume U1 field, whose field strength I denote here by F tilde. And there is a Chern-Simons coupling of the kind that appears in deep brain actions involving the warp volume U1 and the bulk U1. Okay, so it's mixing the two of them like this. So if you have this kind of coupling, then you can consider states like this. You can consider a membrane, make it spherical, make it into some sort of blob, and turn on Q units of flux on the blob. Because it has, because of this coupling, when you turn Q units of flux, this thing gets bulk electric charge. So this blob here is kind of like an extended charge object. It's an extended charge particle. And so it's a candidate that, if Festina Lente is all right, then all the states, including this one, should satisfy the Festina Lente bound. Now, in 4 dimensions, you can actually estimate its mass, just from scaling arguments. And the only scale that appears is the tension. And remember, Festina Lente only works in positive vacuum energy scenarios which are sufficiently long-lived. So you also need to impose some inequality involving the change of vacuum energy. And basically imposing that the Coleman-DeLucia decay tunneling for this kind of domain walls is suppressed enough that the vacuum is long-lived. And if you impose these two things and massage the equations a little bit, you get a bound of the Festina Lente type. Okay, you get a bound that you're not able from just the scaling argument to determine the value of alpha, but you do get that these membrane particles would naturally satisfy a bound kind of like the Festina Lente bound. And the point here is that once you have these blobs, you might also just consider neutral blobs with no charge. This is just a scenario. So I'm not, for instance, for these neutral blobs, you might ask, okay, how are they long-lived? Like what is ensuring that these guys are long-lived? If you want them to be the neutrinos, you need to answer these kind of questions. But at the level of this talk, this is just a scenario, a possibility, a very simple natural mechanism in string theory for Festina Lente to work. Okay, so Festina Lente is actually it's a fun conjecture to work with because it's very constraining. So you don't need to work hard to get interesting statements. It doesn't like very light charge stuff. And what does have very light charge stuff? Well, non-abelian gauge theory. You get the massless gluons. So Festina Lente is in contradiction with non-abelian gauge fields whose masses are lower than the Hubble scale. That's something that could have happened. And yet in the real world, it doesn't happen. All non-abelian gauge fields that we know of are either confined or Higgs above the Hubble scale. In fact, much above the Hubble scale. And it will be very interesting to try and sharpen these arguments to try and get this bound closer to, like QCD or something. So it's just, it's another thing that could have gone wrong, but it kind of works. And you can actually start pulling from this thread and you get interesting stuff. So because more generally, like if there's like hidden, scalars in the standard model, you start moving in the scalar configuration space of the standard model or extensions of it. Festina Lente prohibits that there's any phase of the standard model with unbroken electroweak symmetry. It's explaining why the W is massive, in a sense. And a very nice concrete thing that you can try and that you can use Festina Lente to rule out is what we call the cowboy hat scenario for the Higgs potential. So here on the left, I drew the familiar Mexican hat potential for the Higgs, and I drew two gray bands here and here. Those two gray bands are the only region that we have access experimentally. Like experiments at colliders, they tell us about the quarter coupling and derivatives and so on, but only around this region. We don't know what happens at the origin of the potential. Of course, this is the only renormalizable choice. It's the most natural one. But maybe it's not so crazy that you would have like a cowboy hat scenario where you have a minimum here where the electroweak symmetry is classically, I mean, by the Higgs web is unbroken. You still break it with quark bilinears. And we took those effects into account, but the long story short is that when you take everything into account, Festina Lente puts bounds on the Higgs potential, and this kind of thing is not allowed. So this minimum here really has to be fine-tuned to very tiny values comparable to our current value, so for it to be compatible with the bound. Okay. And actually, you know, this is really experimental prediction. Like this, if we could probe these kind of things, this scenario would really rule out the Festina Lente bound, and that's not so crazy thing. So there's more that I could say about phenomenology. I haven't talked about inflation. That's a super interesting setup. Also dark matter, and all of that is kind of, it's work in progress. Although I can talk a little bit more if I ask about it. I would like to use the last 2 or 3 minutes to say a few words about anti-brain uplift scenarios. Like what happens when you try to apply Festina Lente to, you know, KKLT, large volume scenario kind of construction. So all these scenarios, they have in common, they have this warp throat at the bottom of which you put an antibrain, and the basic idea is that you can decouple the analysis from here to the analysis to the bulk of the Calabi-Yau. Okay, so there's a very natural thing to, so if this logic of decoupling suggests that things like the weak gravity conjecture are not going to be very interesting, because the weak gravity, you know, when you decouple gravity, just an M climb to infinity, it just becomes a trivial bound. But the Festina Lente bound, interestingly, is not like that. When you write it in terms of the vacuum energy, there's no M Planck in the formula. So it actually becomes a non-trivial statement in flat space. Now, of course, it's not a statement about any model where gravity is decoupled, because if you remember, for Festina Lente to hold in the first place, you need to work these conditions in the potential. And to keep track of these conditions in a reasonable limit where you decouple gravity, we couldn't do. It's very difficult. But we did identify some set of assumptions under which the Festina Lente bound is satisfied also in flat space models. And these assumptions are satisfied by the Klebanov-Strasser throw. So what I'm saying now is that away from asymptotic limits, if you for a moment picture that you could have like a slow rolling potential with a long throat like this, you can check Festina Lente there, and you can check it just with the throat, and you can check it, you know, now it's a full top down checking string theory. So that's what we did. We checked actually Festina Lente and also the weak gravity conjecture. Someone should correct me if I'm wrong, but I think nobody checked the weak gravity conjecture for the antibrain in this kind of scenarios. So we just did that. So this is a zoom in of the throat. So Festina Lente and weak gravity are about what are the charge states. So there's 2 kinds of charge states, like strings that end in the antibrain and leave the throat. Also, you can have M-F1 strings that end on a D3 wrapped in the A cycle. And by the way, this kind of scenario where you have the strings ending on the D3 and wrapped on the A cycle, when you work out the details in effective field theory, this is exactly the membrane particle scenario that I was describing before. So in the effective field theory, the way that happens is that you have some membranes, you have some NS5 brain, which is the same membrane that mediates brain flux annihilation. And if you instead wrap it like a spherical membrane, it can get this kind of charge precisely in this scenario. So another way of saying is that this guy can polarize to spherical NS5 brain. So those are the 2 kinds of charge states, and you can just go ahead and check Festina Lente and weak gravity, and they give you some bounds involving the dilaton, the value of the dilaton on the tip of the throat, the length of the throat itself. But there are constraints that are both automatically satisfied for reasonable values of the parameters that are often used in KKLT and Antibrain uplift scenarios. So the stuff on the throat, so that, you know, for the stuff on the throat, the decoupling logic here really works. You know, it's just like you're kind of like decoupling them from the rest of the bulk, so you can really you can really analyze it as if it was kind of like a non-compact model, and sampling constraints are automatically satisfied. However, even though it's easy to decouple the throat from the bulk, it's not easy to decouple the bulk from the throat. Because Festina Lente should apply to anything, any stuff that you can have in the compactification. And, you know, in the usual effective field theory logic, there's nothing wrong with you having like, you know, another stack of brains really far in the Calabi-Yau, and you can often engineer these guys in such a way that they get, for instance, like non-abelian gauge fields that don't confine, Or if you have several stacks, there will be a U1 linear combination that is not killed by the Green-Schwarz mechanism, is not made massive by the Green-Schwarz mechanism. And so these kind of scenarios are very much in danger of violating Festina Lente. For them to not to violate Festina Lente, you need the antibrane to be able to communicate its effects arbitrarily far away in the Calabi-Yau. You have a huge Calabi-Yau, and you put the antibranes on the other end of it. Still, Festina Lente tells you that these effects, at least this strong, so precise numerical values, should propagate all the way to the other side of the Calabi-Yau. So it's very much saying that you cannot really have fully decoupled throat from the bulk. So yeah, in that sense, I mean, makes sense, right? Because we're involved in this is a constraint which involves both the vacuum energy and more particle physics-like things like masses of particles. So of course it need to have some sort of decoupling. So I'm out of time. So I'm just gonna flash my my conclusions, which is just like, look, the point of the swampland to me is not just to have a lot of conjectures that we can check and be sure they work in the control setups of string theory. It's also to learn the principles, because learning the principles allows us to extrapolate, to apply them in situations where otherwise we wouldn't know what to say. So just from studying black hole decay, you get this bound, which has a lot of implications. Of course, we need to know if it's correct, or not. And still there's many implications to be worked out, but I cannot wait to see what people are gonna do with other principles, other swampland principles that you can in principle try and extend, and apply in regions of moduli space or configuration space beyond those which we can directly check in string theory. And with this, I thank you very much for your attention, and I finish.
All right, thank you, Miguel, for the very nice talk. Let us all thank Miguel with our clap emojis. Our first question is from Ivano.
Yeah, hi Miguel,
Ivano.
Nice seeing you. Very nice talk, and also very nice paper. So I was wondering, so at the beginning you talked about this one of these conditions in order to have ds times s solutions, right? And so it turns out that we found that bound independently, not by working on whether ds exists, but whether ads exists, right? And it turns out that the two are exactly complementary. So either you have ds times s and then you have all this story, or you have ads times s kinds of solutions when you introduce fluxes with runaway potentials and stuff like that.
You see, so this really requires runaway potentials, right? Because otherwise, for instance, if I just put the sitter, in the usual narrow scenario, you guys can still see my slides, right? Yeah. So this is, in this scenario, you can actually have both ADS2 and DS2.
Oh yeah, I was talking about runaway potentials, and in particular, so I'm talking about these stringy models with SUSY breaking of various kinds, where you have these kinds of potentials, and it looks like these conditions for that. In your case, it means that the condition is violated and you don't have this setting. This seems to be rather generic in stringy constructions, as you also said. So I was wondering, how do we reconcile this with, like, this bound is extremely interesting and we can learn all sorts of stuff from it, but if we can't build stringy constructions.
But no, I mean, that's spot on, right? Like, that's precisely why we cannot check, like Festina Lente. So first of all, like the kind of construction you're talking about, like, are these like so first of all, Festina Lente seems kind of like effective field theory kind of things. So for instance, the vacuum energy should not be of order the string scale. There should be some separation between these two things. But I agree with you. We don't have concrete constructions of this. And so this is why Festina Lente is a little bit out on a limb. On the other hand, we'd better be able to get something like this. We better be able to get something with positive vacuum energy, or this also applies for slow running. It doesn't have to be the sitter. Like if it's running slow enough that it can describe the real world, we need to get that. Like I better believe that that's somewhere in the landscape.
Right. Well, there is an interesting alternative in the very heterotic model you cited. So it turns out like there is this runaway, but if you put on fluxes, you stabilize the dilaton and you get ADS. So you say like, okay, it's ADS, we can't do anything from it. But actually the brains that nucleate in ADS satisfy the conditions that, allow these brain world de Sitter kind of thing.
That's right.
So
Yeah.
maybe that's a viable alternative.
You mean like the
I'll
stuff
stop talking because you don't want.
this is the stuff that Ulf has been doing a lot, right? Like
yeah, exactly. And we have the stringy embedding of the.
Yeah, actually, I need to understand a lot more about those models because I don't really know. Like again, like Festina Lente is about you having like a rising Russell black hole. I don't know to what extent because, for instance, in this model, it's difficult to localize gravity to the brain, and so I don't know. But yeah, definitely.
But you can find all the details in the in the papers. Okay, well, thanks a lot.
Thank you.
All right, our next question is from Iran.
Hello, thanks Miguel and also Isabel for the very, very nice talks. It's really very interesting work. I wanted to ask about the Festina Lente bound. That one thing that is curious to me about it is that it seems to become trivial when G goes to 0. Which is somehow the opposite to all the other Swampland ideas, behaviors, or in the sense that it certainly doesn't seem to be any sort of obstruction to global symmetries. And somehow the weak gravity conjecture decay is tied to the no global symmetries from infinite entropy for black holes and so on. So do you have any thoughts about this, or what does it mean? Or
so I agree. That's a weird feature about it. I don't think I have a good answer. Look, I can tell you like the obvious thing that when G is going to 0, on one hand, like the narrow branch is going very much to the right. So that's like just like a technicality of how it happens. Perhaps something that can be said is that there's I had like this magnetic version of Festina Lente that gets to this bound, which is telling you that if maybe the limit that you're discussing can be obstructed. So you cannot send G to 0 while you keep V finite. But on the other hand, of course, you could just say, what if I just do the two things at the same time, right? And then yes, you're right. I mean, it doesn't seem to be related in any obvious way to any principle about global symmetries, and I agree with you. That sets it apart from basically every other Swampland constraint. Well, maybe not every other.
Yeah, but because also like a magnetic, if I did a electromagnetic duality on it, it would still be trivial when G goes to 0, no? Because if I do because I have to replace the monopole mass with a cutoff over G squared, and then I get something. Is that correct? Or
so with sorry. Okay, so if you do electric magnetic duality, then you end up getting so we did this in the paper when you do things carefully, because you need to take, instead of the electric field of the narrow black hole, you need to take the magnetic field, so you end up having basically the same bound.
The same bound.
Right. And if you're talking about the magnetic gravity, the one with the cutoff, right? That this is what it is.
Yeah.
And just say that the cutoff, magnetic gravity cutoff, is bigger than H, and you get this.
Okay. All right, thank you for.
Thank you.
Okay, well, if there are no further questions, let's thank.
May I ask one more thing? Like, maybe more of a, you said one of the things you said is, the bound applied to U1 electromagnetism basically explains why the W is massive. But I think that's not quite true. I mean, I agree. It does tell you that electroweak symmetry needs to be broken because of the fermions. But if you are in the broken phase, then all you have is an SU2 factor and a U1 hypercharge factor. And I agree, the fermions are less charged and the unbroken U1 hypercharge, but not the SU2 adjoints. So I agree with you on the counts of the fermions, but I think you said something about this predicts why the W has to be a massive.
Oh yeah, you're right. I just meant that that massless and abelian fields are Look, I agree. So okay, I was careful the way I said it. The fermions, they break electroweak symmetry. So that's where I was going. So if you have unbroken electroweak symmetry, then it goes against Festina.
Yes, of course. I mean, the one I don't know if to call it loophole, or in all of these, including, you know, what I've done sort of to do with gravity conjecture is, you know, you could also read, you're saying like, you know, the CC is connected to the weak scale, the Higgs wave, but why is it not to the Yukawa couplings, right? Like that's always always a loophole in any of these.
Hands down. Like for instance, this 10 to the minus 90, yeah, of course. That's because there's a Yukawa there that we don't really understand. But you know, even if I just do it with the W, it's not so bad still. Like, you know, it's still like it's not as good, of course.
It's not as good, but yeah. So this is always like the thing that is kind of a little bit annoying. Like
no. But this is a great point, of course. Like it is true. Like there's a bunch of things that we don't understand. We don't understand any hierarchy in the standard model, right? So I would say anything that reduces the number of hierarchies to understand, I think is good, and that's
for sure. Yeah,
that's doing that.